Hello, everyone. Welcome back. One midterm and one massive internet outage later, we are halfway through the course. Wow. Time flies when you're having fun, right? Anyway, the midterm or term test marks should be returned to you by the VW date, which is like sometime next week. The markers have got it managed. And also that massive outage, you may have heard of CrowdStrike being all over the news. It's the cause of the outage is still it's still not completely pinpointed, but rumor has it it was due to a null pointer dereference caused by a malformed data file that their code didn't properly check. So yeah, do well in this course. Don't be like CrowdStrike. I'm just going to turn the microphone volume down a bit, and then we'll get right into it. We're going to do some more stuff with strings today, so please have that ready. But before that, we're going to talk a bit more about design by contract. So we have the same learning outcomes as have been in the last few lectures. We're going to talk more and more and more about ADT, abstract data type, and separating interface versus implementation. Like I said, we're going to talk more about design by contract, and also we're going to basically dive deeper into the string example and actually make a second implementation of the string data type that uses the same interface in order to demonstrate how different implementations that work in very different ways internally are interchangeable once you separate it from the interface. And then we're probably not going to get to this one during this class, but if we don't, we certainly will tomorrow. You've probably, hopefully, noticed on the assignment by now, you have to make your own test cases. So I'm going to tell you about test cases. Simple enough. So, like I said, we're going to go deeper into the string example. But before that, there's a quiz, open question thing about design by contract. So, go into Menti, and once this works, I'll have you access it on your devices. We're basically I'm going to show you all a function signature, and you all will be tasked with thinking of preconditions and postconditions for it. And very silly is that the star notation, like the asterisks that denote pointers, if you try to put those in Mentimeter, it just makes text show up in italics. So like, there's this function that returns a pointer, but if I put it on the slide, it just shows up as returning a primitive and being italicized. So my super cool pro workaround for this is to just split the window. Hopefully this is visible enough. I'm sort of stalling for time for people to join by talking about this, but this function, you can imagine, would be a potential part of our string interface, where you take a string and indices for start and end, and you return a pointer or a newly allocated substring of that string. And as you can imagine, hopefully imagine, there's a lot that can go wrong with wacky values we might not expect for each of the parameters. So I think I've rambled enough, and that the player count has remained stable at around 17 or 18. So let's get into it. I think I just have to restart the presentation. Please don't look at the answers. Okay, I'm relieved that I didn't kick you all out. It's go time. Oh no, you don't see the function prototype anymore. If anyone needs help seeing the thing, let me know and I'll dedicate more screen space to it. Cool. So of course there were multiple correct answers, and looks like most people got the first one. So start must be greater than or equal to 0. Yeah, pretty self-explanatory. If it's not, then you'll probably trick the function into accessing memory before the string, and that's a very bad idea. No one caught end must be greater than or equal to 0, but that's a thing too. In fact, I would go a bit further and say that end must be greater than or equal to start, because, well, you can't, or those aren't valid indices for a substring that way. S must not contain an empty string. Happy that no one chose that one. We would call that an edge case. More on that tomorrow when we talk about testing. It's not what you'd expect from most common use of the method, or the function, but it is perfectly well defined. Start must not be null. While it's true that we generally don't want to be given null values to our functions, and we should usually check for them in our preconditions, start is just an int, and ints can't be null. Conditions like these only apply to pointer types, not primitives. And s must not be null. Same explanation as why start must not be null isn't a good idea, but the opposite thing. S is a pointer to a string, pointers can be null, and you don't want to be like CrowdStrike. Excellent work. So, looks like most of you are really getting it, so I won't spend too much time on these explanations, but S is not modified. Yeah, if our substring method changed the input, that would be weird, because that isn't what it's supposed to do. Start and end are not modified. Those don't matter for these primitive int values because they're copied when passed to the function. Technically, the pointer is copied too, but the thing that it points to is not. It's like pass by value versus pass by reference that you talked about when learning Java. The return string is valid or null. Nice. null is a totally acceptable return value for if something went wrong. Return string is always null. Yeah, that would be a dumb one because that would imply that the method always fails. The return string contains part or all of the original string. Yeah, that's a substring. You guys got this. Dadaugen me. Nice. Now, this one's just a sort of open response. Try to think of other preconditions for this function. I already named one during my explanation previously, and that one would be a perfectly valid response, but see what you can think of. Yep, n greater than start and n is greater than or equal to start. I would say the greater than or equal to precondition is more valid because you might want to get a substring of length 1 that just has the same start and end. End is less than or equal to the string's length. Yes, make sure it's valid. End is greater than strlen. Yeah, same thing. End greater than start. Agreed for reasons mentioned earlier. Yeah. Input equals expected input. Not completely sure what that means, but that's interesting. You may be getting a bit ahead of all of us and thinking of test cases. So I think you're onto something. Nice. I was actually just about to say, y'all have great preconditions to do with the indices, but try to think of the string pointer. But that's exactly what someone just did. So the input, doesn't contain null byte. I misread that as is not null, which is a good precondition. I would say that the input, assuming by that you mean the string pointer s, probably should contain a null byte because strings in C are typically null terminated. That stupid null byte test case in assignment 1 is definitely out of the ordinary. So I don't think it even matters too much, actually, if you're not ever iterating through the string. If you're using strlen, it would. But whether it really is good to check for that or not, that is an interesting answer. Door is locked? Well, don't see any people around, so. Oh, because there's a car. Yeah, I hate it when that happens. Same thing. Try to think of some post conditions.
I have a question.
What's up?
In industry, how many preconditions or post conditions for something like this would you actually do?
Ooh.
Would you actually do these exhaustive lists?
Good question. I think in industry, it generally focuses more on tests where it would be as exhaustive as this. Design by contract isn't as common in practical use, but I still find it's a good thing to know about because you would usually end up thinking of preconditions and postconditions while debugging. So, yeah, answer to your question is basically it is this exhaustive, but in different contexts. Ooh, excellent postcondition. Yeah, if the substring is somehow longer than the original string, probably screwed something up. Good call on the valid string. That probably means null if something went wrong. Otherwise, I don't know. This could be a different string implementation from our string examples. So whatever invariants you defined for the string type should hold for whatever you return. Yeah, this is all good stuff. Awesome. Yeah, like assuming the string is implemented using an array, which, as we'll see soon, might not always be true, but assuming that it is, there definitely should be a null byte. Microphone's not even on. Hello? Hello? Okay. Notice that a hair fell into it, so that might have been the cause of all those noises. Good answers generally. So it's definitely worth repeating that design by contract is specifically about preventing programming errors. Once the program is built and into users' hands, the role of design by contract is over. Congratulations, Magical Rhino. That's a very strange looking rhino, but it definitely does look magical. I think those booming noises aren't me. I turned off the mic and they continued. So, back to strings. Maybe if I just hold the microphone, it'll be less horrible. So we're going to keep building on the example. At this point, we've started the private interface to go with our private interface is a little weird, but it refers to what functions there are accessible to just the string file, like stuff labeled private in a class. We have some design by contract enforced with assert. We have some behavior that a user of the string can call. We have header guards to prevent the parts of the H file from getting defined twice when including the file in multiple other files. And we dove into dynamic memory allocation to avoid some of the resource management problems that we encountered earlier in the course. So what are we going to do today? Why do we still care about strings? Well, we did dynamic memory allocation. We're going to kind of sort of add more behavior. You'll see soonish that part of our interface sort of won't fly for different implementations. But we're going to talk about another little safety feature that's very useful in C and beyond, const. And then we're going to do something really stupid. This example just gets more contrived by the minute, but we're going to make another string implementation that uses a linked list instead of an array to store the characters. I want to be very clear that I am not endorsing this. This is a very bad idea, and the takeaway should not be, hey, maybe you should store strings as linked lists. The reason we're doing this, such a stupid thing, is to show off how one interface can have multiple implementations. The array string and the linked list string will work quite differently under the hood, but anyone else using the thing doesn't need to care about the details whatsoever. So yeah, when you're learning from this, don't think about arrays don't think about strings being implemented with linked lists because you'll lose brain cells. Think about different implementations for the same interface. So we're going to think of a hypothetical post condition that we might implement in one of our methods. Let's go back into Aviary. So this idea could apply for any of our functions / methods, but I'm going to do it with get contents because it's so short, and I wouldn't have to do any wacky jumping around big blocks like we have for a char at. So one potential programming error that you might want to prevent, even though get contents is sort of the most straightforward thing ever, imagine perchance this is a more complicated method, is that the method does not modify the string whose pointer is passed to it. So in order to prevent, or rather catch the error when it happens of get contents changing the contents of string, or at least what the object is, we could possibly keep a record of what were passed. I'm going to say self before. And then just to make this slightly more complicated, I'll say that this is now a variable called toReturn. And then who knows, maybe we're just on a really cursed C implementation where reading the contents of this data structure somehow modifies it. So we might do assert self before self after. Though actually that just compares the numerical pointer values. If the pointer itself changes, that's not a very big deal. We care about the memory pointed to by the pointer. So let's just do this to compare the actual things being pointed to. Oops. So yeah, if we were really paranoid, we could do something like this.
I just have a question.
Yeah?
Does self after need to be declared before its use?
Oh, totally. In fact, I didn't even mean to call it self after. I just want to compare it to self again. Good catch. Although, for reasons I'll be about to discuss, we're never actually going to run this code because there's a way easier method of doing this exact thing. So, what was I saying? You could be paranoid and take a copy of your pointer and just make sure that it points to the same thing as before. But do we have to? Yeah, it turns out it is overkill, and we can use a C keyword that exists in like every language ever, every good language. I don't think Python has it. Const. So const tells the compiler this value will never be changed. So we could go ahead and spam the U key to undo. And just do const string self. And that does the exact same thing, much more concisely. So I'll go ahead and do it to the other getter. And char at shouldn't modify it either. So let's add that in here too. But notably, destroy string deallocates the memory, and after that, there's no guarantee about what the pointer points to. So we don't need it here. Same idea with make string, which literally creates a string which necessitates modifying it. So you could probably see, actually I guess you could put a const on the input because we're making a overkill struct string out of a regular old char array string. That doesn't modify the input char array. So yeah, let's get into the weird stuff. So like I said, please don't think about the practical implementations of this. You should not use a linked list to store a string. Do think about how we're going to pretty much completely change how the string works internally with almost no changes to the interface that other coders can use. I'm just going to move this because maybe the weird noises are caused by friction with the overall. Oh, yeah. I guess before we should do that, we should change the interface to align with our changes that we made to do with const parameters. So let's do that quickly. Also, I added some comments to the H file. The way that it works is identical to the one we've been using for the last few classes. So don't worry about copying these comments down. But after this lecture, when I upload the current state of the example to UMLearn, this file will sort of act as a sort of a model solution. Just a good example of how much commenting you should do when making a header file, like the H file for the implementation. So we decided that makeString takes a const char. We didn't modify destroyString. And then every other method takes a const pointer to the string struct. Also on Vim, you can repeat your last action by pressing period. So the last thing I did, like the last mode I switched to, was insert. I typed const and a space, and then exited insert mode. And then pressing period does all that again. Really convenient when you want to make the same change over and over. And then one more preliminary step. Actually, there's going to be at least two more. I'm just going to rename string.c to stringarray.c to make it more clear what it is. Yeah?
So I have a question. Using this const keyword, is that something like we should be doing just for design by contract, or just moving forward in C with methods?
Moving forward with everything, really. Like, a lot of the lessons in this course are admittedly pretty C-specific, but const is in a lot of languages, and you should use it all the time so that you don't accidentally modify things that you didn't mean to modify. So we've got a fresh start with a new file, and first thing we're going to do is include our header file. Cool. And now I know I did say a couple times that you shouldn't pay attention to the specifics at all, but it just so happens that on assignment 2, the implementation of the struct data structure can be pulled off using either an array or a linked list, or maybe even some other data structure that I'm not thinking of. But to get full marks, you need to use a linked list, and that's because just using a linked list will give you more experience working with pointers and stuff in C, so it's more educationally useful. So this example might be quite helpful for anyone who needs a refresher on how linked lists work. So before we write the structure for the string, we're going to make one for a node of a linked list. And we're going to forward declare it to make the definition a bit simpler. This is sort of what I meant by private interface earlier. Even though those words sound like they should contradict each other, this is an implementation for a string data type, but it also includes a node data type, sort of both the interface and implementation for it. It's a very simple data type, so we can get away with that. Plus, it doesn't have any use outside of the string. But if this were a more complicated project, I think Node would have its own header and code file. So yeah, refresher in first year comp sci. A linked list is made up of nodes, each of which contains a pointer to the next node and whatever thing you're holding. In this case, a char. And then we're going to use this node type to make our string struct. This is different from our struct string from before, which previously had a pointer, and I think it also stored its own length. Yeah, it did. So now it's a different type, probably has an even different size, but through the magic of interfaces, we'll be able to work with it in the same way. So we'll do a invariant check first. You don't have to name it check invariant every time. In fact, it might be better to give it a more descriptive name specific to the type you're writing. So let's say check string. Oh yeah, and let's forward declare string with a more convenient name, like we did earlier. And also, I'm just going to change this to title case for consistency. So what might be in our invariant? Well, certainly the pointer should point to something. And its length should be a non-negative number. But even this is kind of redundant. Very similarly to how we did the sort of clunky thing of making a copy of the struct as it existed at the start of the method and then comparing it to the struct at the end of the method. But then it turns out we could just get that for free by using const. There's a better way to test that a number is non-negative, or rather to guarantee that a number is always non-negative. And that's to, well, first delete that and use unsigned types. So this came up earlier in the course, but I wouldn't blame you for forgetting. Unsigned integer types, and I think unsigned floats exist too. They are always greater than or equal to 0, so they can't represent negative numbers. This is another lesson that's sort of generalizable to different languages, and another reason why I really don't like Python. When you can replace explicit error checking logic with just intelligent use of a language feature, do that. It'll make your code simpler and also more idiomatic, so like doing things the way of the language that you're using. And I'm just going to put a comment for here. Self is non-null. The thing passed to assert is pretty self-documenting, but I want to be consistent for conditions that are more complicated. So another thing that should always be true for our string type, rather our specific string implementation, is that we should have the right number of nodes. So the value of length should correspond to how long the linked list is. This is a pretty standard iteration through a linked list. Feel free to copy and paste it into your assignment if you need a quick refresher on how to work with them. Because, hint, 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 maintaining the number of items currently in a stack and maintaining the number of items currently in a stack and having an invariant to check that that number of things reflects the actual number of nodes in your linked list is a very good idea. I'm kind of writing part of the assignment for you, huh? Good thing the tests are way more important than the intricacies of what a stack is. That's what Comp 2140 is for. And I'm not going to help you with that. I'll tell you all about what tests are, but examples? Nah. we're just going to keep going from node to node to node to node until we get to the end of the list, which is represented by a null pointer. And then finally, we assert that the length is the same as what we just computed. Oops. Self length equals count. The stuff I'm doing here is certainly not the only way to do things. You could make your invariant check quite a bit simpler by sort of moving this logic to wherever you need to access the length. You could even remove the length property from the string struct and have string just be a pointer to a node. And that would be equally valid. However, I think this structure is a good idea, where we have length as a variable and our check string function to manually check that it has the right value, because it ends up simplifying the rest of the implementation. We don't have to call some compute length function whenever we need the length. And that also speeds up the implementation decently if we're not doing that loop every time we need the length. A single variable access is way faster than iterating through a linked list. So it simplifies the code both conceptually and in terms of performance. Next up, the code for putting a node in the linked list. All right. There we go. That's the function signature. This is another private function. We actually haven't even done anything to implement the string interface aside from providing a definition of the string type. But we will get to things like char_at and getLength later on. Note as well that self, the string pointer, is not const this time, because inserting a character into a string necessitates modifying that string. So don't just throw const everywhere, because, yeah, on occasion you'll need to make changes to the objects or structs you're given. So preconditions. We don't really need any, just that the invariant holds. Char can be, or to add can be literally any value. I guess you could specify that it is within the range of printable characters, like it actually represents a number, letter, or punctuation mark. But if the user somehow enters some other characters, that won't actually cause any trouble. So you could chalk that up to being more of an edge case, something that doesn't happen often but can happen, it is allowed, than a programming error, which actually isn't allowed. This is just linked list stuff. We'll get back to programming practices eventually. Recall malloc from earlier. We're allocating on the heap as many bytes are necessary to hold an instance of the node struct. And this also means that we're responsible for freeing it later when that memory is no longer needed. These will be required for iterating through the list. We're checking for null because malloc is not guaranteed to succeed. It may not be able to allocate the amount of memory you want. So yeah, a whole bunch of this will just take place within this if statement. Did I call the character C? I just want to check. Yeah, I did. That's a bad name. Yeah. Did I use C anywhere else? I guess I'll find out when I go through the compiler errors. When we allocated space for new node, like using malloc, the values of its properties were just whatever. On some C implementations, it might be all zeroed out. It should be for security reasons. You don't want to have a really clever program that accesses memory it shouldn't by exploiting the other way it could be initialized. Because the other way it could be initialized is that those properties would just have the value of whatever happened to be in memory at the time. So yeah, initialize your variables. So we just have a special case to deal with. If the linked list is empty, so it refers directly to null, we make this the first one. Let me know if I'm going too fast, by the way. I will try to talk about this, and then doing so, give people, answer your question in a moment, give people chances to catch up. But there isn't always that much to talk about when we're just reviewing stuff from first year, so I might not do much talking while going through this example. What were you wondering?
I'm just a bit confused. So you make new node with memory allocation size of node. How would new node be equal to null? Like in what circumstance would that happen?
Oh, that's if malloc fails.
Okay.
So yeah, not enough memory, can't allocate it, it just returns null. Who knows what I was writing there? I think I was looking at the wrong line of my notes. Implementation note, we're going to use while, but we could also use the length of the string to do the same thing, like the length property, which we check in the invariant is correct. So when we're out of this while loop, the current variable should point at the last node of the list. Or sorry, null, so that previous points at the last node of the list. So, like I mentioned in the introduction to design by contract, preconditions and postconditions apply to parts of your code, which usually means functions, but can also mean loops. And in this case, our loop has a postcondition. So we want previous to actually point to something, and for the node that previous points to have a next property that points to nothing because it's at the end of the list. Highly recommend drawing a diagram if you're writing code like this for yourself and you get confused. There's a lot of like little bits of indirection you have to do with previouses and nexts. Then finally, insert the node. Bada bing, bada boom. So we end the case for the node, the list already being populated. And then we just increase that length property to reflect the fact that we just added a character. That's actually the only pre or post condition we need for this one. Especially since check string will already check that the length property is still valid for the size of the string. I suppose we could also record the length of the string at the start of the function and then make sure it's increased by 1 at the end, but that's not technically a valid post condition because that won't always happen. New node returning null and the whole thing failing is a perfectly valid scenario for how this function would work. So at the end of the method, we can't really make any assumptions about the state of the node or state of the string, since insert end may or may not actually work. And that's reflected in a lack of post conditions. So let's actually implement that interface.
Question.
Yeah?
So if malloc did fail, then the string at the end of the day after calling that function just like would be the same.
Sorry, what did you say? This string, something, something calling the
We're
function?
adding a character to the string, right? But we use malloc for that node.
Yeah.
So if malloc does fail to allocate, would the string just end up being the same?
Yeah, exactly. Let me just check the interface. We will actually have to make some changes to the interface to make this work with both arrays and linked lists, but we're going to try to keep those changes minimal in accordance to the whole idea of being able to use different implementations without requiring people working with that code to know much about the implementation. Okay, make string takes const char star input. We'll define our preconditions first, as always. Also note that when you're writing your own stuff, you'll probably think of preconditions and postconditions as you go. But it's actually a really good exercise / technique to actually think of those preconditions before you write any code, because going through that process in your head will help you think through how the function will actually work and probably stop you from writing some bugs on your first pass. I want to say valid because C strings are weird. Let's just say non-null. And we're going to also assume that the input string is null terminated. And sadly, there's no real way to check that assumption. You might think maybe you could call strlen and make sure it returns a sensible value, but how would you check what a sensible value is? Unfortunately, that assumption is uncheckable. Although you could get around it by making the interface slightly more complicated, passing in the length of the string as a separate parameter, and checking that a null or the end of string character exists at the end of the string as defined by that length parameter. But we've already made our interface, and I only want to make changes to it that are absolutely necessary for functionality. So we allocate memory for the string, and we do some initialization to it, but only if my string isn't null. And then we just call our insert end function over and over. Oh wait, parameter order. It's always good to put the pointer to the struct you're operating on, almost said object there, first, because that's what most closely matches other languages' conventions of like dot notation. It makes it clear that you're operating on this object rather than, this struct, rather than that struct being just some parameter that represents input to the function. And it's what every object-oriented language does internally anyway. Yeah, that's our constructor. One more thing, actually. We need to return my string. Just going to rewind a bit and talk a tiny bit about comments. The .h file had pretty thorough comments, and it sort of acts as a little usage manual for the interface. So in the implementation, you could copy and paste the comments, and you might want to do that on assignments anyway, just to be safe. But another thing you could do is just C string.h for usage. And this is pretty smart because it puts your documentation in only one place. If something changes about how the method works, you don't have to make that change twice. And even better, when you inevitably forget to make that change twice, well, doing it like this prevents that situation entirely, so you don't even have to worry about what happens when that happens.
Should a check string be on my string itself?
Yes, good catch.
And also, do you need to use like the arrow for like my with like my string and like?
Yes, thanks for that too. Did I use the wrong thing on my notes? No, I just screwed that up. Thanks for catching those. You saved us some time for when we compile this. Oops. I might be able to finish the destructor in the next 2 minutes, but if not, I'm totally willing to just stop this lecture in the middle of a function, and then we'll pick right back up from where we left off next time. Last time the destructor was pretty simple. We just had to take care to deallocate the array as well as the struct that holds the array. This one will be a bit more complicated because we have to deallocate space for each node of the linked list individually. This is another thing that you can and should copy and paste for your assignments because we're not actually teaching you about linked lists. The stuff about testing is way more important. Oh, I forgot the preconditions. Oh, my time's up. Yeah, lecture's over. We'll continue from here next time. Have a great day. Bye.